So your hook today consists of how to make a device which would power your radio if you were stuck on a desert island. Another example of physics making your life better or saved. But before we get into building this device, we have now moved from the study of static electricity into the study of current electricity. And I would like you to put on your worksheet what you feel that difference is. How does current electricity differ from static electricity? And now I'm going to tell you what I say. So I hope you stopped the show until you had a chance to write. But static is, of course, not moving, and current is all about the movement. That indeed we did move charge around in static electricity. We rubbed it off of one place and onto another. And it was, you saw in the case of the capacitor lab where you got a shock to go through you. You can take static charges and get current to flow, but only for an instant. I want continuous flow. And so that is going to take new mechanisms, different from the ones we use, the tribo methods that we used before, rubbing electricity off of one place and onto another. And this historically begins with the work of Galvani, who discovered that with a dead frog, if he touched it with two different metals, these metals are touching here, that he could get the frog to kick. And that, of course, freaked people out. It's like you're bringing the frog back to life. And here you have a cartoon where people are using what is in fact a battery to bring this corpse back to life, which you would see is really the work of the devil, that it is God who is supposed to give life, and here you are, human beings. And this is, after all, what Dr. Frankenstein does when he wants to give his monster life, is he gives him electricity that comes from a lightning strike. But soon after Galvani's work, everybody was fascinated by it. Another Italian named Volta, Alexander Volta, discovered that you could do it without living tissue. It has nothing to do with life. I mean, it is how our bodies work, but it is not the magic of life that you are uncovering here. You will have a chance. I will give you two different metals, and I will tell you that I'm giving you frog skin, but in fact it's just going to be cloth soaked in salt water, which is what Volta did. And he took copper and silver, and he put brine-soaked felt in between them. This forms what we speak of as an electric cell, and it will, as you will see in class, it will give rise to a potential difference. The chemical behavior here will cause there to be a potential difference between the two. And this time, if you pull a current off, you put a wire between these two, then the current will flow, but the chemical reactions will tend to keep restoring the potential difference, and so we can now get a continuous current flowing. That the smallest unit that will do that is called an electric cell, but if you take two electric cells and put them together, then you have formed what is known as a battery. Battery has to do with multiple, and I expect you to know that vocabulary. So I just want to illustrate this. I do not hold you responsible for anything that happens on this page aside from the idea that you have these two different conductors, and because they are different, they have different affinities for electrons. We call it electronegativity. If you put silver and copper together, then the silver will steal electrons from the copper. If you then put a wire between the copper and the silver, current will flow, but if you want to maintain that current, you really need these chemicals in between. You need that salt-soaked brine in between. The most common, and we call these batteries here in the United States, but they're not. They're cells. You put two of them together, then you have a battery of two cells. But this is really a cell, an electric cell, and it used to be that they were made up of manganese and zinc were the two different conductors that you dealt with. And there was a reaction like this, that we had ammonium chloride in between, and the zinc would react with the chlorine ions to form zinc chloride, and those electrons which had been on the chlorine ions get left behind on the zinc. So this cup, which is made of zinc on the outside, and I'll pass these around so you can see them, would become negatively a low potential because of those electrons. And then at the manganese dioxide, which was making up this gray region here, you would have reaction with the ammonium of the ammonium chloride, and there you would have two electrons taken away from the manganese dioxide. This rod here in the center is carbon, and ultimately it is the zinc and the carbon which form the pair and give rise to this electrode, this anode, being positively charged and or having a high potential, and this copper cup having a low potential of the cell. That because it is carbon and zinc, there's a difference of 0.74 between them. But that is going to be true for each of these electrons. Because you have those two electrons involved, then it comes out to be about 1.5, which is true for all carbon zinc cells, and that is true for the alkaline batteries, and that is true for the older style batteries, which now they call heavy duty to make you feel good about them, but they're not very heavy duty. Here is another example. I don't hold you responsible for these reagents or these reactions at all, just the concept of differing electronegativities leading to the electrical potential that we develop. This is one that has lead and sulfuric acid. Here's the other part of the sulfuric acid. In addition to lead, the other conductor is lead dioxide. And again, you get this chemical reaction with electrons taken away or left behind on those two things, and hence the potential difference. In this case, the difference in electronegativity between those two ought to be 1 volt, and 1 volt for two of these is going to be 2 volts, because a lead dioxide cell is a 2-volt cell. And we put 6 of them together. This is a car battery, and that's the 12-volt cell, and I will let you see that there in class. So, a battery or cell is one example of turning a different form of energy into electrical energy. And in this case, it's chemical energy that gets turned into electrical energy. Can you fill in these 3? We'll tell you in class, but I'm curious to know if you can fill in these 3. If you're very clever, perhaps you can do the piezo crystal, but I feel free to leave that one blank. That's stretching you a little bit. I want to go back to the topic of analogies. That when we talked about voltage in our study of static electricity, we said that it was analogous to potential energy that exists because of the difference between the two plates. Indeed, voltage was equal to the work done per charge moved. So it was like energy, but it's not energy. That's only an analogy. that in fact its units are not joules, which would be the case if it were energy, they are volts. Now I introduce another analogy for voltage. EMF, which stands for electromotive force. That voltage is like the push that makes electrons move. Ah, excellent. I understand voltage very well now. Yes, it is like, but it is not. It is not a force, or its units would be newtons. Okay, so you have this push, and the result of the push is a current. And I want to talk about that. Here I have a picture of a wire where, again, in the sense of analogy, I have made one end higher than the other, one end higher gravitational potential than the other, but it's only an analogy that this end of the wire has higher potential, this has lower potential, and so it's going to push the current through the wire. Our understanding of current is not how fast does the charge move through the wire, but rather how much charge moves past a point in the wire. So here is our equation for current. The symbol for current is I. The reason we use an I is from the work of Ampere, who would talk about current intensity, but in French that's intensité du courant, and so he used an I. Over in England they were using a C for current, but Ampere's notation caught on, and so we use an I for the symbol for current, and we're looking at how much charge passes a point for each unit of time. The units of current will be amps, actually amperes, but we shorten that to amps. Capital A is the symbol for the units, and they are equal to a coulomb per second. Next comes Georg Ohm, who said, you know, if this push is what's making the current flow, then if you had less push, there ought to be less flow. Indeed, if the potential difference between the ends was half as big, then there ought to be half as much current flow. This was his PhD thesis. Much to my surprise, his advisors thought it was crazy. But it's not crazy. It's exactly what he discovered to be true, that the voltage is proportional to the current, and that is what is known as Ohm's law. If we write that as a proportionality, we introduce a constant of proportionality, and we use an R, standing for resistance, to being the constant proportionality. Different wires would have different resistance to the movement of charge, and so there would be a different constant proportionality, but for all those wires, it would be the case that if you doubled the voltage, you would double the current that flows. It's very important that resistance is a property of the conductor. It does not depend upon the voltage or the current. Typically, we will write this when we mean to talk about Ohm's law, but it seems to imply that there's a relationship between voltage and resistance, and there is not. Doubling the voltage does not double the resistance. Doubling the current does not have the resistance. Resistance does not depend upon I or V. It's a constant that depends only on that wire, that conductor that you are sending the current through. Things which obey Ohm's law are called ohmic. And I would ask you on this graph to make a picture of what the functional relationship between current and voltage would look like. Now that you've done that, we look at my contribution, and I hope you drew something like that. If you didn't, then fix it. But let me see that you made a mistake first. That it's a proportionality. That's true for ohmic devices, but it turns out there's a number of substances which do not obey Ohm's law. Some law, that is. If you don't obey it, then you don't have to obey it. But there are a number of materials, and we're grateful that there are, which do not obey Ohm's law. They are non-ohmic, and they have a graph that looks like this. That there is a region where as you change the voltage, there is no current that flows. The resistance here is very, very large, near infinite. And then there comes a threshold voltage where suddenly the resistance goes away and it's almost like there's no resistance at all. We say the device turns on. This is what semiconductors do, and that's why they're so useful in all of our electronics. That you have an electronic switch. Using only voltage, you can have it be turned off and no current flows, or be turned on and the current flows easily. So there's your on, off, your 0, 1 of computing. Okay, I would ask you to go through this list. We said that resistance depends only on the material. What qualities of the material do you think would lead to maximum resistance? So please fill this out and then restart the program, and I hope what you got was that in the choice between long and short, longer would have more resistance. After all, if it's hard to get through a wire, then it's going to be harder to get through more wire. Thick or thin, I think, will be a little bit of a surprise to you, that thin has greater resistance. And if you think about the appliances in your house, where you have a big appliance like a water heater or a dryer, it's got a great big thick cord on it because it's going to draw a lot of current, and we need to keep the resistance way low or it'll overheat. In the choice between kinked and straight, it turns out it doesn't matter, which is unfortunate. That our symbol for resistance is going to be this, like an obstacle course, that it's hard to get through. But it turns out that's nonsense. That's the symbol we'll use, but in fact there is no difference in the difficulty of getting through a straight wire and getting through a kinked wire. Hot or cold, it turns out that hot offers greater resistance. When you make things colder, their resistance goes down. If you cool things very dramatically, we get into what's called cryogenics, where we can make the resistance go away altogether. We can have a superconductor. But hotter does mean more resistance. Copper and aluminum, it matters, but you would have to make a guess. It's all empirical. That it is important that you know that what material you're working with does make a difference in the amount of resistance, but you just have to be told or know which one has higher resistance. Color of the wire does not matter. Although we have these black and red wires, they both carry current equally well. Okay, so the property of the wire, here you go. Here is the resistance, the formula for the resistance of a wire. It depends upon the length of the wire. It depends upon the thickness of the wire, that's cross-sectional area. And it depends upon what material the wire is made up of. This quantity rho is called resistivity. This is resistance, here's resistivity. That's a property of the wire, so the material of the wire. What is missing from this is the temperature, and I will show you how to get there in just a minute. You need to memorize the factors which contribute to the resistance of a wire. They are the material, the cross-sectional area, the length, and the temperature. And I also expect you to know what direction it goes as you make the length bigger, or the area bigger, or the temperature bigger. I think this mnemonic works a little bit better. It's got those E's in there for electrons that are moving around. Instead of cross-sectional area, it's got diameter. But I think you could work with it. One way or another, you must memorize this formula. Do it now. Here is a table that you will work with in the book. Here's the resistivity. Notice the units, that after all, if resistance is equal to this quantity, then the resistivity times meters divided by meters squared, that's going to get you ohms. So those are indeed the units of resistivity. Over here you have the values that the resistivity would change by if you raised the temperature. That all of these resistivities are at 20 degrees Celsius. But if you went up a degree, the resistivity would get greater, and this is how much. Notice that for these semiconductors, which there's the resistance of a resistor, here's the resistance of an insulator, great big, and in between are these semiconductors, which have resistivity in between. But notice, when you raise the temperature of a semiconductor, its resistivity goes down. That's wild and crazy. But the thing you do with this, and I do not expect you to know this formula, but this is how you work with this coefficient. You look it up when you need to do that. But you take the resistivity gets modified by this factor, that you take this coefficient and you multiply it by how many degrees you are above 20, and then add that onto 1 and multiply it by the resistivity here to get the new resistivity. So for example, suppose you were working with silver and the silver was at 35 degrees, 15 degrees above 20. Then you would put in the resistivity of silver, and then you would take this 1 plus that coefficient times the 15, and then whatever length and cross-sectional area the silver had. Note that if you were below 20, you would put a negative here, and the resistance would go down, as well as the resistivity. So you do a problem. But before you do this problem, I would like you to practice that memorizing. Will you please make an attempt at writing down the formula for resistance based on material and the other qualities of the wire. And here it is. And now you do this problem. Please notice your units. I think you would want this to be in meters and this in meters. And notice that they have not given you the cross-sectional area, they've given you the diameter. It is a round wire, so you can use the area of a circle to get the cross-sectional area. Finally, here you have a problem. A 100-watt light bulb, which is not atypical, in your living room would draw 1 amp of current. That is 1 coulomb per second passing every point in the wire feeding that bulb. And a coulomb, of course, is big! So the question is, have you ever noticed the electric field when you have a coulomb present? Have you seen the carpet fiber standing up? Have you seen dust and bits of paper jumping on and off the wire? And the answer is no, you have not. There is no electric field in the presence of this enormous amount of charge. And the question is, how not? And I coach you that it is not because the charge is moving. If you took 1 coulomb of charge and went running around the room with it, there would be this enormous field that traveled around with the coulomb of charge. It is not because of insulation. Indeed, if you want to block electric field, what you have to have is a conductor. And you have some wires like that in your house. They're called cables, where the information is going in this wire, and this bit of conductive material surrounds it to shield from electric field, so the information doesn't get corrupted by you running a vacuum cleaner or there being a lightning storm. It is not because the two wires are paired. If you were to peel them apart, you would still be able to run your lamp, and there would still be 1 coulomb passing every point, and there would be no field. So see what you can do with that problem.